Hello everybody, my name is Emilios and today we're going to talk about algorithms in HPX, a high-performance parallelism library for C++. For this tutorial, you'll need a complete HPX installation and know how to compile and run an HPX application, for both of which there are complete tutorials linked in the description. So let's get started. To begin with, let's take a look at this very simple snippet of code which calculates the summation of all integers from 0 to 999. As you can see, this is a very simple script with a for loop that iterates from 0 to 999, and each time it adds the integer to a variable called sum, and then prints the summation of all these integers. If we were to run the script, we would get a summation which is 499,500. But how can we do this with an HPX algorithm? To do this with HPX, we're going to use the algorithm reduce, which implements a reduction operation where a sequence of values is combined in a single result using a specified binary operation. So let's take the code step by step. Firstly, we declare a vector of size 1000 called numbers, and then we fill it with sequential values starting from 0. We then call reduce. We specify the execution policy, so to utilize HPX parallelization, we write HPX execution par. Then we provide an input range, in this case it's the limits of the vector numbers. We set an initial value, here 0. And lastly, we specify the binary operation, here addition. We store the result of reduce in a variable called sum, and then we print it. If we run the script, as you see, we get the exact same result as before, 499,500. I mentioned before that the first argument in reduce is the execution policy. Actually, this applies to all HPX algorithms. But what execution policies do? Execution policies convey guarantees or requirements that the loop body imposes. So passing par in the algorithm means that we ask for parallelization, that it's going to happen only if the loop body can be parallelized and does not contain any constraints that would prevent that. HPX includes all the execution policies that the standard has, which are the sequenced policy, which means execute in order on the current thread, unsequenced, that allows out-of-order execution but on the current thread, which means vectorization, par, which is the one we used before and allows parallel execution on different threads, and parallel unsequenced, that allows parallel vectorized execution on different threads. HPX includes more execution policies, but they are out of the scope of this video. Overall, HPX execution policies provide asynchronous, distributed, and highly customizable parallel execution capabilities that go beyond the limitations of the standard library. Now let's see the effect that some of the execution policies have while discussing another HPX algorithm. The algorithm for each is designed to efficiently apply a function to each element in a given range. So we're going to initialize a vector that will contain our data. This vector will have a size of 10 million. Then we populate this vector with values starting from 0.0 and incrementing the value by 0.01 for each subsequent element. Now we call the HPX for each loop body. First, we define the execution policy. For now, we select the sequential execution policy. The second and third parameter is the first and last iterator, basically the range to which we're going to apply the function. And since we're going to apply it to our whole dataset, we select the first iterator to be the first element of data and the last iterator to be the last element of data. The last parameter is the lambda function we want to apply. In this example, we want to apply the sign operation to each element 100 times. To see what we did, we're going to print the first 10 results and the time it took to run. Running this code, we see that the script takes about 12 seconds to run. Now, if we want to run our code in a parallel manner, we change the execution policy from sequence to parallel. This parallelizes our loop, resulting in a performance benefit of almost 10 seconds, since it took the script 2 seconds to run. Another execution policy, as we saw, is the parallelized unsequenced policy. So to see how it affects the performance of our code, we're going to change the execution policy to par unsec. Running the code shows that this policy is actually the fastest of the three, being only slightly faster than the parallel execution policy. So now that we have discussed how execution policies affect the performance of our code, let's see how more HPX algorithm works. The first one is HPX find, which works like standard find but takes advantage of the HPX parallel execution. So HPX find searches for the first occurrence of a given value in a specified range. Like in the for each example, we initialize our data to which we're going to apply find. To keep things simple, we're going to use the exact same dataset as before. Then we initialize the value that we want to find. Let's say we need to find the value 23. We store it in a variable called value to find, and then we write the HPX find function body. Like before, we set the execution policy to par to take advantage of the capabilities of HPX. Then we provide the range we want to find the value. In this case, we search for the value 23 in the whole dataset data. And the last parameter we need to provide is the value we search for. In the last part of the code, we make a check if the value was found. If the value is found, we print a message that says that the value was found at which index of the range. If not, meaning if we do not find the value, we print that the value was not found. Running the code shows that the value 23 is found for the first time at the index 23,000. The function find works also with characters, doubles, strings, etc. Another HPX algorithm is HPX count. Count works in a similar manner with find, but instead of finding the first occurrence of a value, it counts its occurrences in a given range. So let's see with an example how it works. The first thing we're going to do is create a dataset of size 1 million and populate it with values from 1 to 100 in a random manner. Next, we specify the value we need to count by storing it in a variable called value to count. Like before, we select number 23. Count also works with characters, strings, etc. Applying HPX count, we set as usual the execution policy to be parallel. Then we specify the range in which we want to count 23, in this case the whole dataset data. And in the end, we specify the value we want to count. The output of HPX count is stored in a variable called result. To find out how many times we found 23 in the dataset, we're going to print the variable result. By running the code, we see that the value was counted 9,954 times. Moving on to another application that utilizes an HPX algorithm, in this case HPX sort. For this example, we need to sort a list of students based on their grades. So let's move step by step. First, we define a struct variable called students that holds the name of the students and their grade. A simple constructor is added for convenience. After that, we define a function that prints the name of the students with a custom title. Now let's dive into the main function. Firstly, we initialize a list of students and grades. For this example, we use a list of 10 names and 10 grades. Next, we're going to print the list before sorting and then apply HPX sort. When we're using HPX sort, we have the option to leverage parallelism by utilizing the parallel execution policy like we did with all the examples before. The function of the algorithm is similar as before. First, the execution policy, then the range we need to sort, in this case the list of students and grades, and lastly we pass a lambda function as a custom comparator, with which we compare two objects, in this case student A and B, and we use const so that the lambda will not modify the objects, and we use the operator to declare that we want the largest values first. If we wanted the smallest values, we would use the opposite operator. Then we print the list of students sorted. Running the script, we see that the students is sorted based on their grades as we wanted to. Now let's explore HPX replace. Let's take a closer look at one application. Let's say we have some data from a survey that we have stored in a vector called responses. The responses are numerical values with -1 meaning that there is no response or no data. Our goal is to replace these -1s with zeros. So we print the original responses and then we call HPX replace. We utilize the parallel execution policy by setting it as the first parameter of the algorithm. Then we set the range where replace is going to be applied, in this case the variable responses. The fourth parameter is the value we want to replace, -1 in this case, and lastly the replacement value, 0. And we print the responses after the replacement. We run the script, and as you can see, all -1s are replaced by 0. A slightly more complex example is an application of blur effect on an 1D grayscale image by utilizing HPX transform. The first thing we have to do is define the blur filter function. This computes the average of a few neighbor pixels starting from index. So we define sum and count, and then we're going to write the for loop that iterates around the current pixel. This function is basically a moving average filter, a common type of image blur. Moving to the main function, our first job is to simulate an image. To do this, we define an 1D vector, and we store values which represent the brightness of a pixel. Then, initialize a variable to store the image size. Then we set the blur parameters, which is the window size, and we set it to 3. Now we're ready to apply the blur with HPX transform. We initialize a vector called blurred image, where we're going to store the output of transform. This vector has the same size as the vector image defined before. Now to HPX transform, we select parallel execution as our execution policy. Then we define the input range, which is the beginning and the end of the vector image. Then is the output range, where we're going to store the output of transform. Here is the vector blurred image as defined just before. And last is the lambda function. In the lambda function, we have the capture clause, where we list image size and window size. Capturing this by value ensures that they are safely copied and that no threads will fight over them. Then we represent each element in the input range with value, and we calculate the index of the current pixel with value. We get the address of the element that is being processed, and with image 0, we get the address of the first element of the vector. Subtracting these two gives us the position index in the array. Now we call the blur filter function to compute the blurred value for the current pixel. This returns the blurred brightness value that becomes the corresponding output for the blurred image. Now to see the results, we first print the original image and then the blurred one. Running the script, we can see that the original values that represent the brightness of the image have been transformed. So that was some examples of HPX algorithm applications. For more, you can check the link in the description. Thanks for watching and happy coding, everybody.